So now that we understand that the optimal solution to the sequence alignment problem has to be only one of three candidates, we're going to be easily able to formulate a recurrence, identify the relevant subproblems, and derive an efficient dynamic programming algorithm for the problem. So here is the culmination of our work on the previous video. We thought about an optimal alignment of some pair of strings x and y, and we noticed that there are three cases for the contents of the final position. Either there's no gaps, or there's a gap on top, or there's a gap on the bottom. In case one, where there's no gaps, xm and yn get matched, and we proved that the induced alignment, which is of the smaller strings x prime and y prime, has to be optimal in its own right. In the second case, where the character little x sub m gets matched with a gap, the induced alignment, this time of x prime and y, has to be optimal in its own right. And in the third case, where little y sub n gets matched with a gap, the induced alignment now of x and y prime must be optimal. So one way to think about this kind of assertion is it says that the optimal solution to a problem, to a sequence alignment problem, depends only on the solutions to three different smaller subproblems. One involving x prime and y prime with characters peeled off of both of the strings, one involving x prime and y, and one involving x and y prime. But in all of the cases, all that we care about are subproblems in which a single character was peeled off from the right from one or both of the strings that we started with. And the situation is very similar to in our previous two examples, weighted independent sets on line graphs and the knapsack problem. In the independent set problem, whenever we only cared about subproblems obtained by plucking off either one or two vertices from the given line graph. So all we ever cared about were prefixes of the original line graph. In the knapsack problem, we got subproblems by plucking off the last item and perhaps also reducing the knapsack capacity by some integral amount. So there were two dimensions in the knapsack problem for which subproblems could decrease in size, the number of items and the residual knapsack capacity. So we used two parameters to keep track of the subproblems. And what we cared about were all possible prefixes of the items and all possible residual integral capacities at most the original knapsack capacity. So what's up in the sequence alignment problem? Well, here, subproblems get smaller by plucking a character off of the first string and or the second string. So again, there are two ways in which the subproblem can get smaller, either the first string or the second string. So we'll again use two different parameters, one to figure out how much we've plucked off of the first string, the second one to figure out how much we've plucked off of the second string. But all we care about, the only relevant subproblems, involve prefixes of the two original input strings x and y. That is, the only subproblems that we care about have the form xi, yj, where xi denotes the first I letters of capital X, some prefix of x, and yj denotes some prefix of y, the first j letters of y. So let's now move from the subproblems we're going to use in our dynamic programming algorithm to the recurrence that we're going to use. And the recurrence, really all it does is compile our understanding of the optimal solution and how it depends on the solution to smaller subproblems into an easy-to-use mathematical formula. So I'll use the notation P sub ij for the value of the optimal solution to the corresponding subproblem, the one involving the prefix xi and the prefix yj. And so for a given set of positive values for I and j, what is Pij? Well, there are three possibilities. Case one is where the final position of the optimal alignment doesn't have any gaps. So it matches the final character of x sub I, that is little x sub I, and the final character of the prefix capital Y sub j, that is the character little y sub j. It matches them together and just reuses an optimal alignment for the smaller strings xi minus 1 and yi minus 1. Case 2 is where the last letter of the first string, that is little x sub I, gets matched with a gap. In that case, the penalty of the corresponding alignment is the penalty of a gap plus whatever the optimal alignment is of the first I minus 1 letters of capital X plus the first j letters of capital Y. The symmetrically, case 3, we pay for a gap, and then we pay whatever the optimal alignment is of all of the first I letters of capital X with the first j minus 1 letters of Y. This is the case where the last letter of the second string gets matched with a gap in the final position of the optimal alignment. So we know that the optimal solution has to look like one of these three things. We don't know which. So in the recurrence, we'll just, in effect, do brute force search among the three outcomes. We just choose the minimum of the three possibilities. So that's the formal recurrence. Its correctness really just follows immediately from the work we already did, understanding what the optimal solution has to look like. So before we state the algorithm where we systematically solve all of the subproblems using this magical formula, let's just make sure we get the edge cases, the base cases where I or j equals 0, correctly sorted out. So specifically, what is the value of p I comma 0, and also it turns out p of 0 comma I, where I here is just some non-negative integer. All right, so the answer to this question is the second one is B, and I hope if you could keep the notation straight, then the answer was fairly clear. So let's remember what does Pij mean? That's the total penalty of an optimal alignment between the first I letters of X and the first J letters of Y. So consider Pi 0. So now we're asking about aligning the first I letters of X with the first 0 letters of Y, that is with the empty string. Well, the optimal way to match any string to the empty string is you're just going to insert gaps into the empty string to equalize their lengths. And so if your string has length I, you need to insert I gaps. What's the penalty of that alignment? It's just I times the penalty for a single gap, and that's the answer here in B. So we're ready now to give the algorithm, and as with all these dynamic programming algorithms, once you know the subproblems and once you know the recurrence that relates their solutions, there's really nothing to do. All you do is systematically solve all of the subproblems, moving from smallest to largest. So we're going to use an array A to keep track of the solutions of all of these subproblems. A is going to have two dimensions. The reason for two dimensions is we have two independent parameters which are keeping track of the subproblem size, one for how many letters of X we're dealing with, and a second dimension for how many letters of Y that we're dealing with. That's analogous to the knapsack problem, where we also had two dimensions to keep track of the number of items in play and the residual knapsack capacity. We just figured out what the base case is, so we just solve those in a pre-processing step. So if one of the two indices is 0, then the optimal solution value is just the gap penalty times the non-zero index. And now we just go to our double for loop. It's a double for loop because we have two indices into our array, and whenever we get to a subproblem, we just evaluate the recurrence, invoking the solution to the already computed smaller subproblems. So one sanity check you should always apply when you're writing out the code for a dynamic programming algorithm. When you look at the right-hand side of your recurrence, when you look at these purportedly already solved subproblems whose solutions you're using to solve the current subproblem, make sure you have actually already solved those subproblems. So in this case, we're good to go because the indices of the subproblems are only less than the entry that we're filling in right now. So indeed, all three of the relevant subproblems, A I minus 1 J minus 1, A I minus 1 J, and A I J minus 1, they've already been computed in earlier iterations of our double for loop, so they're just hanging out waiting to be looked up in constant time. And as usual, once you've actually figured out the key ingredients for the dynamic programming solution, namely the subproblems and the recurrence, it's pretty much self-evident why the thing's going to work, and it's also self-evident exactly what its running time is going to be. So why is the algorithm correct? That is, why does it terminate with every entry Aij equal to the true optimal penalty Pij of the corresponding subproblem? Well, this just follows because our recurrence is correct. That's where all the hard work was. And then we're just systematically solving all of the subproblems. So formally, if you like, it would be a proof by induction. So the running time is completely trivial to evaluate. In each iteration of this double for loop, we do a constant amount of work. We just need to look up three strings in constant time and make a couple of comparisons. How many for loops are there? Well, m iterations of the outer for loop, n iterations of the inner for loop. So we suffer the product m times n. That is, the running time is proportional to the product of the lengths of the two strings. So depending on the application, you may be content to just have an algorithm compute for you the NW score, the total penalty of an optimal alignment, or perhaps you're actually interested in the alignment itself. And just as we discussed with independent sets and line graphs, by tracing back through the filled-in table, you can indeed reconstruct an optimal solution. So let me just give you the high-level idea of how it works. It's going to follow the same template, and I'll let you think through the details of why this really works in the privacy of your own home. So assume that you've already run the algorithm on the previous slide, that you've filled in all the entries of this 2D array capital A. Now we want to trace back. So where are we going to start tracing back this filled-in table? Well, we're going to start with the problem that we actually care about, namely the largest problem, A of m comma n. That's what we want the alignment for. Now, we know this optimal alignment is one of three candidates. We know there's three possible situations for the contents of the final position of that alignment. Moreover, when we filled in this entry of the table, we explicitly compared the three possibilities to figure out which one was the best. So, perhaps on the forward pass, we actually cached the result of the comparison, or in the worst case, we can just go back and recompute and figure out which of those three cases was used to fill in this entry. And depending on which one of the three candidates won, that tells us what should be the contents of the final position of the optimal alignment. If case 1 was used to fill in this entry, we should match little x sub m and little y sub n. If case 2 was used to fill in this entry, we should match little x sub n with a gap. If case 3 was used to fill in this entry, we should match little y sub n with a gap. If there's a tie, we get to pick any of them arbitrarily. All of them will lead to optimal alignments. Then, of course, after figuring out what to do in this final position, we have an induced subproblem involving x prime and or y prime. That tells us a previous entry of the table to go to, and we just repeat the process. We again figure out which of the three cases was used to fill in this entry. That tells us how to fill in the next rightmost position of the alignment, and we just keep going until we fall off the table. So what do you do when you fall off the table? Well, once one of the indices, I or j, gets all the way down to 0, now you have no choice. So now one of the strings is empty and the other one has some number of symbols. So you should just insert the appropriate number of gaps to equalize the lengths. One thing that's pretty neat is that this traceback procedure is efficient. In fact, it's way more efficient in general than the forward pass. For the forward pass, you have to fill in every single one of the m times n entries. But in this traceback procedure, each time you trace back, one of the two indices at least will get decremented. So that says you're going to complete this traceback in O of m plus n time with an optimal alignment of the original two strings.